Hey there, APES scholars. We are going to go over the LD-50 pre-lab. LD-50 means lethal dose 50%. So what we are going to be doing is, well, let's get to the next page. The purpose of this lab is to do a bioassay, and a bioassay is just basically a procedure to study either toxic effects of a substance, or on the other hand, it could be testing the positive interactions of a drug might have on an organism. So we're doing this bioassay today to determine the toxicity of salt on radish seeds. And what we're going to come up with is a dose response curve. And so you can see on the right side of the page an example of a dose response curve. And when you look at the LD-50, it's that 50% mortality that you're seeing right in here. And that 50% mortality, it shows you that, okay, at that point we're going to have 50% of the organisms that are dying and 50% of them not dying. But then when you get beyond the 50%, look at the area under the curve. Look at how quickly it increases. And there you get to the mostly dead area. And so basically the LD-50 is it's a good marker for dosages for either toxicity or for effectiveness of a drug. Now, data table. Your data table that you need to be setting up in your lab book might look something like this one, where you've got a concentration of the salt, and you can see that we've got 0 through 3%, and it's a percent salt solution. And so the first one, the 3% solution, was very easy to make up. I mean, it's just 3 grams of salt, and it was dissolved in water, and I added water into a graduated cylinder until it went up to 100 milliliters. Now, the other two things you're collecting data on will be the percent mortality and then the radical length. That should be root length. So anyway, so we've got root length and we've got mortality. And the mortality calculation is pretty easy. We're going to have 10 seeds, 10 radish seeds that we're going to be growing. And if 4 of your seeds do not germinate, they are mortality. They're categorized as mortality, and then the percent is pretty easy. It's just 40%. Now, please understand the purpose of the control. The distilled water is going to be the control. And if we have if we have a significant portion of the distilled water seeds not growing or dying, then we know that something was wrong with the seeds, or perhaps there was something wrong with the measurements, but I don't know how I can screw up a 0% distilled water. But that could happen. So anyways, you've got your control, you've got your data table, and it's probably going to look a little bit like that. And you'll need to set that up because there is not a data table that is in the lab itself. So you've got to have that set up so that when we get the data, and I think it's going to be on Tuesday that we get data, you'll have it. Now, preparing the saline solutions, I'm going to ultimately have you do some calculations here because I think it's instructive to look at the calculations that if you were actually in the classroom doing this lab, you'd have to do this part. And so you would be given the 3% stock solution, and then you'd have to do some dilutions, and you would have to produce the 2.5%, the 2%, the 1.5, all the way down to the 0.01%. And it's very interesting when you look at how much of the stock solution is used. When you get down into those lower amounts, it's a really small amount of the 3% solution, and so they're really mostly water. Well, and actually that makes sense because we're doing a dilution thing. So I've shown you an example of the calculation on how you prepare a 2.5% salt solution. So basically it is that M1V1 equals M2V2 that hopefully you remember from chemistry, and the M is molarity, and the V is the volume, so M1V1 equals M2V2. You can also substitute in percentage, which is what we're going to be doing. So it's percent times the volume and then equals the percent times the other volume. So when I set it up to solve for the 2.5% salt solution, So if I want to make 10 milliliters of 2.5% salt solution, that will equal X milliliters of the 3% solution. So basically, when you solve for X, that gives you 8.3 milliliters of the 3% salt solution that you pour into a graduated cylinder, and then you add distilled water until you get it up to a 10 milliliter total. Now, I want you to calculate the other amounts of 3% salt solution you would need to make each of the other 8 solutions. So you've got to calculate the 2, the 1.5, the 1, all the way down to the 0.01%. And that needs to be in your lab book. And then this is what it's going to look like. We'll be setting this up a little bit later today. And you can see that there's some Petri dishes. And over here are the paper towels that are in the Petri dishes. And basically, what I'm going to be doing is adding just enough salt solution to get a damp paper towel. I don't want to make them overly wet. And if they get overly wet, then you could have some fungus coming into the system, and that would throw off our results. So we just want to dampen it enough so that the seeds will be able to germinate. So I believe that would be it. Get the pre-lab done, and tomorrow in class you will see a setup of the data, and then on Tuesday you'll be given the results, and so we'll be looking at the results on Tuesday. So good luck with that, and I will see you all later.